All right. So then, without further ado, let me introduce Luc de Raedt. So Luc has an ERC Advanced grant on automated data science, so he's a perfect speaker for this. He is actually my predecessor here in Freiburg. He had the machine learning professorship here in Freiburg before moving over to Leuven. In between, there was Martin Riedmüller, who went to DeepMind and was on the Atari project. Now it's me. So we have this connection, and Luc also has far too many awards and so on to list, but yeah, he is a EuroAI fellow, AAA fellow, HKI trustee, and so on. And I'm super stoked to hear him talk about automated data science. Luc, all yours. Thank you.
Okay, thanks, Frank, for the kind invitation and introduction. It would have indeed been a great occasion to come back to Freiburg, but unfortunately, my schedule did not allow for that. So I'm very pleased to talk about the automation of data science. And as you will notice, I'll approach it from a quite different complementary perspective as automated machine learning, because what you guys are doing is really looking at big data sets, a lot of computing power, whereas we're really trying to find a niche in looking at small data sets, but making it available to the naive end user. But let me first start with the introduction and acknowledge some of my people that have been involved in that. The introduction to automated data science is based on a paper written with colleagues Tijl, Jose, Holger, Porek Smith, Joaquin, and also Chris Williams that just appeared in Communications of the ACM earlier this year. And then there's a lot of people that contributed to the ARC that are listed here. The motivation, in a sense, for my interest in automated data science is really the kind of AI perspective. I'm very much an AI researcher, and in AI, it has always been the case that we were wondering, can we build a machine that does X? And then people have gone by starting, X equals game playing. Can we build chess playing programs? Can we prove theorems? Can we do vision, natural language? And then, of course, it's quite natural to also ask the question, can we do science? And there is this project called The Robot Scientist by Ross King and colleagues that was making quite some impact about 20 years ago. And what they did is actually automate scientific reasoning and experimenting in certain branches of the life sciences. They actually had a theory, and they also had a robot that could carry out experiments. And what they were then doing is the robot would design the experiments and would carry them out. And depending on the results of the experiments, they would actually revise their theory. So it was very much an active learning setting that was doing theory formation in the life sciences. And they had two versions of that, Adam and Eve, functional genomics, and one for drug screening. Now, if we can do data science, then of course, if we can automate science, as Ross King and colleagues did with this robot scientist, then of course, the question is, can we also automate other branches, such as data science? And that is, what we call automated data science. It would actually be quite useful to be able to do so, because if you look at one of the reports by PricewaterhouseCoopers of a couple of years ago, then they basically say that automated data analysis is second on the list of potentially most impactful AI techniques for business. So if you can automate that, that would be quite useful. And of course, data science is in a sense broader than just machine learning. So we organized some workshops at Dagstuhl and also at ECML PKDD together with Tijl, Jose, Holger, Porek, and Chris. And we also wrote this overview paper then on the basis of that. Now, if you look at data science, then there is typically a couple of stages that you can distinguish. In the first phase, you'll probably be in the bottom left, of these 4 quadrants, and you'll be exploring your data. You'll try to understand what the data is about, what the task is that you're going to tackle. You're probably going to play with data. You're going to visualize. You want to get insight. And then there's like a second phase, which is typically this data engineering phase, where you want to put the data in the right format. You want to transform it. You want to integrate it. You want to do some data wrangling techniques to kind of make it ready for machine learning. And then you want to build your models with typical machine learning systems. And of course, then there's all the tasks that AutoML is so good at, like algorithm selection, parameter optimization, and so on. And once you've built the right model, you also want to exploit the results in the real context of the end user. That means you want the model to give insight to your end users. You want to make predictions. You want to build systems around that. Now, if you look at these 4 quadrants, then there's like 2 dimensions that matter. On the one hand, there is the dimension where you can have more or less dependency on domain context, on domain knowledge, so to say. And you'll see that when you explore the data, also when you exploit your models, there is typically a strong influence of the domain that you're working in. The particulars of your application, of your data set generation will allow you to use and exploit knowledge and context. On the other hand, techniques such as data wrangling and model building, they kind of don't really depend so much on the domain. I mean, it's kind of standard techniques that apply everywhere. And then on the other dimension, which is like from left to right, the task can be pretty well defined or can be very open-ended. And so data engineering and data exploration are very open-ended. Certainly data exploration, it's very hard to know what the data scientists are looking for when they start analyzing given data sets. It's very open-ended. On the other hand, if you're running a machine learning algorithm, you know what kind of model you want. It's very precisely defined. It is not at all open-ended. And so you can distinguish these 4 quadrants along these different dimensions. And it already indicates that certain tasks are going to be harder and easier to automate. On this picture, it's clear that model building, which doesn't rely on the main context and which is kind of less open-ended, is kind of the easiest to automate, whereas data exploration, which is very open-ended and which relies a lot on the domain context, is going to be very, very hard to automate. So let me go through these 4 quadrants in just a couple of slides. But before doing that, let me also mention that you can look at, when you want to automate these processes, you can look at different levels of automation. And the first one is really this mechanization, which is what AutoML seems to be focused on. You basically want to run this without kind of human involvement, or with as little human involvement as possible. And a second kind of level of automation is like where you typically have kind of workflows, or you kind of integrate pieces of code and then reuse and couple them together. And that's like compositional. It's what you find in standard data mining, data science techniques like RapidMiner, 9, Weka, and so on. And also what you find in the kind of programming language support for machine learning like Stan, TensorFlow, and so on. A final level is where you really try to monitor what a human data scientist is doing, and you want to assist you want to provide assistance with those tasks that can be easy to automate. And of course, that's going to be a way more interactive kind of endeavor. As I said, automated machine learning is the least open-ended and the least dependent on the domain context. It is assuming that the task is pretty well defined. You want the inputs to be very clear. You want the loss function to be typically very clear. And then you want to find, the best machine learning model that tackles this task. And it's really cast as a crisp computational problem, a kind of optimization perspective. And so from the application side, it's already assumed that all the pre-processing steps, all of that is in a sense already solved. As you know, and as you certainly will hear much more later this week, there are several sub-problems where AutoML has been extremely successful. The results are really extremely interesting and applicable. This is really technology that can be applied as is. In contrast to the techniques in the other three quadrants where things are way more open than in AutoML. And problems that have been successfully tackled include searching the architecture, looking for hyperparameters, doing meta learning. This is really very mature, state-of-the-art machine learning technology that can be used off the shelf. I don't think I need to explain what all these hyperparameters and search and techniques are. I guess that is pretty well known, and you'll hear much more about that later this week. One technique that I find quite fascinating, because it's a little bit different than the standard AutoML techniques, is the automated statistician. Because there, again, it's a very well specified task. I mean, there's like time series, and there's also a model space that is being defined. But what it then does, it produces this kind of statistical model. And in addition to doing that, it actually also produces a paper that describes and explains the model in statistical terms, just like the kind of report that you would get from a statistician doing the analysis. It's also a beautiful system in the sense that it combines a kind of search methods for the right models and model components, combining kernels in particular ways in order to arrive at very, very nice fits and curves. There is the next quadrant, which is exploitation. So that's like the bottom right. So it is really dependent a lot on the domain context, and it's also less open-ended. It's really about exploiting the models. And it really is about also like interpretability, about trustworthiness, about giving reliability estimates and stuff to that in the specific application context, which could be, for instance, a medical application where you really wanted to build this kind of system that uses the model, the machine learned model, to assist your medical doctor. The most open-ended quadrant is about data exploration, and there is numerous techniques that allow you to get insight into the data. Things like visualization are being used, PCA, clustering, pattern mining. And the thing is that it's very hard to kind of formulate an objective criterion to really do this data exploration task. Nevertheless, there are some works like from my colleague Theo de Bie that is really trying to formalize what is meant by this subjective interestingness. Subjective meaning it's interestingness according to the end user, that should be formalized in a sense. And he talks about 5 steps in this. It's typically applied to pattern mining. That's the context where he has been looking at the most in the kind of data mining context. And he says like there is typically 5 steps in there. First, you have to choose like the form of the patterns that you're interested in. And then you need to formalize this measure of interestingness. And that's typically the hard task. What is interesting or not will depend a lot on the eye of the beholder. And you notice that when you work sometimes with biologists, they will say, well, I will know when you found something interesting when I see it, but you typically want to get some kind of hard criterion to be able to build an algorithm that will find these most interesting algorithms, these most interesting patterns. And you then want maybe to visualize it, to facilitate interaction, and maybe to kind of reiterate. And he gives like several examples. He's been working on that for many years. And for instance, in the context of communities, where you see like this little toy example on the right, you can wonder what is most interesting. Is it the fact that, you know, some of these nodes are densely connected, like the orange ones? Is it that it's a large clique? Is it that there's like few neighbors outside the community? Are there some other specific kind of properties of this? And then what he also says is that, yeah, he actually formalizes this interestingness, he calls it subjective interestingness, to what the prior expectations of the data analyst are. And for instance, if you already know the degrees of the nodes, then probably the most interesting pattern is not the orange one, but it's actually the purple one, because it's the most surprising pattern in there, according to yeah, the kind of subjective interestingness that he would then derive. And so it's what's interesting is relative to what you already know, to your prior expectation. He's got all of that well defined. There is like, yeah, a framework that has been devised about 10 years ago, but that has since then been applied in many different contexts for many different types of patterns, you know, like this kind of communities, but also like other things like typical item sets. The key idea is actually that there is an initial background, that distribution that will give you, you know, it will devise the patterns over, it'll be kind of maximum entropy distribution according to the prior beliefs. And then when you get new insights about, you get new knowledge in a sense, then you'll kind of condition that on further beliefs, and you'll get a kind of new distribution according to which you can see what is the most interesting. Let me give an example. I mean, this is like a good old-fashioned item set mining, so probably not that interesting, but just for the purposes of this kind of presentation and this kind of idea, it's something that's relatively easy to explain. On the right, you see like the typical kind of abstract data sets that you could have, where you have documents and words, and then you can look at like which patterns occur frequently in there, and then you see these are the patterns that occur frequently in there, and that's pretty uninteresting actually. Now the next step that he then does is like there is prior expectations, and the prior expectations would basically be that the sum over the different columns, like number of occurrences of words, a number of words in documents, so the row sums and the column sums, that these are known in a sense. And then you can define a kind of maximum entropy distribution to look at where are these surprising elements, and you can then relatively to that kind of mine for the patterns. And then you see that you get a much more interesting set of patterns already, a much more meaningful set of patterns. And you can then condition that even further by looking at knowledge that you typically have with such conferences, which is like keywords. I mean, there's indeed like a lot of patterns in there that you would expect if you know the keywords, and so that in a sense are unsurprising to anybody understanding data mining. And so what you can then do is like, if you assume the keywords are also known, then you can again filter according to that and get, you know, the kind of right patterns that are probably more interesting and more surprising to the end user. And there's a lot of further work on that. Okay, let me now look at data engineering, which is like this other quadrant. There's again a lot of different subtasks. There is data selection, there's probably data fusion, wrangling the data, and that's what I'm going to focus on a little bit. And then also like things like feature engineering and anomaly detection. One system and approach that really opened up a lot of work on program synthesis and automated data wrangling is a seminal contribution by Sumit Gulwani at Microsoft. What he was doing is actually, he was showing for the first time that programming by example and program synthesis could do something useful, because that's now a feature that's actually incorporated in Excel. It's called flash fill. And what it actually does is, like, on the basis of one or two examples, you'll typically learn a string transformation program that will take a set of inputs, a set of strings, and will produce another string. Typically, the thing that you'll get is like illustrated here on the right. I don't know, can you see the arrow, or?
Yeah.
Can people see the arrow or not?
Yes.
No. Okay. So what you'll get is like this date that needs to be transformed. And so you get like classical dates, and then on the basis of one or two examples, you'll actually give hints as to what the desired format of the data should be. And then what is learned is a string transformation program that takes some of the left columns and actually produces the desired string. And so you can, for instance, learn to look at names where you have, for instance, William Cohen. You could kind of abbreviate that as CW, the initials. You could then take Frank Hutter and abbreviate it as HF, and probably you would find a program that would do that. But if you then come at my name, which is Luc de Raedt, you get like 3. So should it be DL or should it be DRL? And so you probably have to give, one or two extra examples to learn the string transformation program correctly. Now, that was a hugely influential development, which is now constantly used in kind of approaches to do data wrangling. Because you typically, it often happens that your data resides in spreadsheets or in other ill-formatted data forms, and you want to transform it into a kind of tables, tabular records, or so on. And here is like another example, Flash Extract, one of the follow-up systems, where you could indeed like show positive and negative examples of desired and undesired transformation. And again, it would learn to find the correct one after a couple of these transformations. And that's like something that's quite fashionable, and the line of research is continuing today. What people are doing in recent times, in the past 2-3 years, is combine it with foundational language models. Here you see this domain-specific language that FlashFill was using in the initial days, and it was actually doing a kind of standard search that was focusing really on a relatively simple, and that is then guided by machine learning methods to do the ranking and to find solutions quickly. But it's also pretty limited, because if you just look at syntactic transformations, and you would give the example, with DEC, you give December, and then with Nov, you give November, then, well, what it would produce is like October, January, and so on, which is, of course, from a program synthesis perspective, if that's all you've seen, it's kind of the relevant thing to do from a purely syntactical point of view. But of course, you would want it to take into account knowledge that we have. And so in recent years, people have coupled that with these language models. There's a system called Flash GPT-3 that would be able to produce the correct transformations. It would recognize that these are months and would give the correct output. It would also be able to, on the basis of 2 examples for India, New Delhi, and for France, Paris, it would be able to find, it would be able to complete this last column automatically. If you're interested in those things, I would recommend you to look at the website at the bottom. There is some talk by Sumit. You also find the talk by Tail the Bee on this automated data exploration that's online actually. Other examples that work with this language models are transformations like the ones you find here. On the left, you see like how many mice does your cat catch, and then you turn it into kind of this exercise where one word is taken out and goes from plural to singular. And then you can actually see that it will complete this full column on the basis of 1 or 2 examples. It will actually find the right ones by coupling syntax and semantics in these these language models. Another thing that I wanted to briefly mention in this automated data engineering is the search for the right features. And I know that AutoML has, of course, quite some features and work on automated feature generation. But here it's a little bit different in the style of sports analytics, where there's a lot of time series coming from my colleague, Jesse Davies. And what you have in sports analytics is that there is quite some time series that are connected, like something with, for instance, the movement of your right leg and your left leg, and you'll typically get the kind of time series that you have there. And what you notice in these, that the original time series, of course, you cannot really adequately process them with the machine learning models, and so you typically need to do some transformation, some feature generation. There is some observations that Jesse and his team made, namely that if you handcraft features starting from these time series and this type of data, that you get features that can really improve the performance a lot, and that typically requires using a bit of domain knowledge, like the fact that it's the left and the right leg that is being measured, and that there's a lot of time spent on coding this. The typical story that data pre-processing takes 80% of the time in the machine learning process, and then or in the data science process, and that many of the current tools are insufficient because they have limited abilities to keep with to deal with this low-level data. And so what they have produced is a kind of automated approach that would start from sets of features, time series like that, and they would derive like these features in a couple of steps. They would build a kind of computation graph in which they first would derive a couple of new series, and then from these new on these new series extract some predefined features and actually select the relevant ones. So here at the top you see well, the inputs, the raw data, so to say, and then the next level is that they would define some kind of combinations, like, for instance, a ratio between 2 time series. And then next level, the purple one, where they would construct new features as like operations on these time series. And they would, again, continue like that, get this kind of computation graphs, and ultimately they would end up with a set of features. Of course, there would be a lot of feature selection going on there as well in these search methods. So they start with kind of empty graph and then rapidly build that up by adding both new compositions, adding both new series, and then like constructing features and attributes on top of that. And they have then methods to filter out the relevant features and also avoid redundancies and stuff like that. If you're interested in that, please contact Jesse Davis on that. Okay, so that's for a short intro to this 4 quadrants of automated data science. What I'm going to do in the second part is show a little bit what we have been up to in my ERC project, and that's basically, in a sense, the opposite perspective as what AutoML has been doing, in the sense that AutoML has been focusing a lot on the model building aspect, focusing a lot on like big data, on very advanced machine learning methods, actually for people that already understand machine learning, whereas we've been trying to build it something simple to really naive end users, very much in the spirit of flash fill and the things around that. Also, if you analyze the 4 quadrants, I've argued that AutoML, the learning task is known. It's the least dependent on domain knowledge and context, and it's also the least open-ended. It's the best defined, and that also explains why it is the one where the automation is working very well at the level of this mechanization. On the other hand, the hardest one is the automated data exploration, where there is relatively few results. Ultimately, you want something interactive, probably there, some kind of assistance. So what we've done in my ERC project is we exclude the hardest part, and we try to combine, both the data engineering, the model building, and the exploitation together. So we want to partially automate this full process, and we do assume that the data still needs to be pre-processed. It's not yet in the right form. There is a data wrangling step that is needed to take place, and we use techniques from inductive programming, this programming by example in the style of Sumit Gulwani's flash fill for that. We also assume that the learning task is not really specified, and we wonder whether we can automatically determine the relevant one. That's basically the setting. And that's the setting called SINT. That's the term that we use actually. So what is SINT actually doing? We're given a data set, and that's a set of tables in a spreadsheet, because there's a lot of data around that takes this form. And then we also assume that there is some partial new input to that data, and maybe that the end user wants to autocomplete that data. He wants to fill out the missing data, maybe make some predictions of possible values. And we do assume this naive end user in this regard, actually. So the SINT setting is really trying to democratize it. It's really trying to bring data analysis to the level of spreadsheet users, which have often a lot of data. It's typically not the kind of big data that you view in machine learning, or certainly not in automated machine learning, because most of the data sets are small, but there's some challenging things in there. We also assume that there is this systematic user, in the sense that you cannot just enter data anywhere in a spreadsheet. There needs to be some systematicity, some regularities before you can actually transform it. And of course, your data must also be such that there is some interesting patterns, some interesting models that you could potentially find to make certain predictions. That is all what yeah, that's the kind of assumptions that you need to make in this context. And then there is some desiderata. Ultimately, what you would like to get is like the no-hands approach, the mechanization, but that's of course extremely ambitious, and that is of course also up to debate. That's a very long-term view. But from a user perspective, you want that the end user just sees the spreadsheet. He doesn't really need to know what's behind it. He just can manipulate at that level. So it's really bringing things to the naive end user, democratizing it. Here is a little example of such a spreadsheet that you might see. This is data about players in a particular competition, the NBA competition. And you see that this could be the way that naive end users could format their table. If you look at this kind of table, you'll see that there is several challenges in there. One challenge would be, yeah, there's some of these data. Maybe you want to predict the points and the salary of this player on the basis of the other data of this guy and of what's in the table. You can also see that standard methods won't directly work on that, because on the one hand, this is wrongly formatted. It's not like typical attribute value or variation thereof. Secondly, there is certain things that are quite obvious for us. The fact that there is this foreign key relations between these two levels of player names in these two separate tables, so to say. There's also the fact that points, for instance, are averages. Like you have 4 values for the different seasons, and then in the bottom table, it's just the average that is listed. What you can also see is that certain constraints hold, like this RAB is just the sum of the 2 other columns, and also that is kind of useful information that you would like to take into account in such cases. If you look a little bit more careful, then what you would also notice as a human analyst is that there is like the 3 rows where something special occurs, something kind of unexpected. If you look at this points level, you see that, well, in the second row for Leonard, you see a pretty low value. It's the lowest value of all, and it's actually almost a factor 10 lower than any other value in that column. So this could be an anomaly. On the other hand, you see also that the one indicated with a red line, that there's extremely low values, but still a reasonably high points level. And so you can wonder, are these the right kind of values? It turns out actually that it actually turns out that there was a typo in the red value, and that then also some of the other values need to be changed because of that. So what we're going to do is like look at a kind of phase where you can process all of this. You can go through data wrangling. We're going to spend some time on constraint learning, and then on building a model to kind of answer that question. It's really a combination of data engineering to cope with the wrong formatting, and then learning and reasoning and model building to kind of compute these values and these corrected values in a sense. Again, it satisfies this very much. We want to make that available to the naive end user and, in a sense, help him analyze his simple data. And the vision there is that you would like people that are Excel users be able to use this kind of tools later on. What we've also spent a lot of time on is like constraint learning in these data sets and also in other data sets. There's a lot of constraints that hold here are, for instance, the sums, this fact that there is foreign key relations, that there is averages. All of that are like constraints. In Excel, it corresponds to kind of macros that you can write down. But in many other domains, like, for instance, in scheduling and in rostering, there's a lot of constraints that hold. And also there is a lot of data available about the past performance. For instance, in hospitals, head nurses at regular times, typically every month, have to make the schedule for the next month. And the way that they do that is, well, they will typically look at what happened last month. They will make some changes. And then there are certain constraints that need to be satisfied. For instance, the fact that, certain free days for particular nurses have to be respected. The fact that you can't do too many shifts in a row. There's some legal kind of constraints and stuff like that. The fact also that you need of certain types of nurses, you need the right composition. You typically need one that's responsible, then maybe two emergency nurses, one maternity nurse, and so on, in a sense. And so also that is something that we're going to analyze. Here you've got one schema of this nurse rostering, where there is like on the top, there is days, and then we have like shifts, like morning and afternoon shifts, and night shifts. We have the nurses, and while the bottom is like the new schedule that the head nurse needs to produce. The top one is like that of the past performance of the past months. And the question then is, can you in a sense learn constraints there that will allow you to fill out that table in a meaningful manner? And the answer will be yes, you can indeed detect constraints that will actually that are actually satisfied by the past schedules. And if you then pass on these constraints together with the input data for the bottom table to a solver, you'll be able to fill this table and kind of proceed like that. And also that is something that we've devoted a lot of time to. There's actually three components in our SINT system. One is about this constraint learning. The other is about automated data wrangling in the style of flash fill. And the last one is really this auto-completion, where we try to use both predictive models and constraints. Now, with regard to constraint learning, it's amazing that in the AI and machine learning community, everybody is actually using constraints, but relatively few people are actually looking at learning models for constraint satisfaction problems. Certainly in combinatorial optimization, very few people are really looking at how they can be learned from data. And yet there is such a big demand for that, because operations research is such a big area that's massively applied in industry and business. And there's loads of data around that could be used to improve models that are now painfully extracted from, by hand, typically by interviewing, in the old-fashioned ways. So constraint learning from a machine learning perspective, and there's a lot of tutorials and stuff that and overview papers that we've written about that. That's together with Stefano Teso and Andrea Passerini and Samuel Kolb and others. If you look at constraint learning from a machine learning perspective, well, it's just applying machine learning to a kind of new setting. The kind of hypothesis, kind of functions you learn are different than what you typically have. And that gives a couple of new challenges. And it also yields typically explainable models. to the simplest possible setting goes actually back to Leslie Valiant in his seminal CACM paper on pack learnability, where he was showing that you could learn, this CNF expressions, this KCNF, in the probably approximately correct manner. And what he then had is like, you have the class, and he would only look at positives. I mean, his first result was for learning positive, from positive examples only. And he would then learn things like that, that would, like the theory that you see here, which would be kind of constraints. So on the basis of this binary examples, you could learn a logical description in the form of a conjunction of disjunctions, this KCNF format, and he proved that this is kind of probably approximately correct learning. And that's the very simplest form of constraint that you can think of, because you have like Boolean variables and you have like logic to express the constraints. Now, whereas Valiant was doing that in a kind of, enumerative fashion, you can also use other methods, and you can look at extensions for doing that. Here, what we learn is not this conjunctive normal form, but we use that in what is called SMT, so satisfiability modulo theory. That's like this Boolean CNFs extended with inequalities and numbers, this LRA domain, and you can then express things like B should be less than 0.4, and a disjunction between two other inequalities should be holding. And so you can get then positive and negative examples. And the question is, can you come up with such a formula in this format that will classify most of the positives, well, most of the examples correctly? And one version of constraint learning is really that you can not only use a solver to compute possible solutions to this kind of constraint satisfaction problems, because that's the general way in which these solvers are used within AI. But what you can do is really like encode your problem also as a constraint satisfaction problem. And so what is done in this InCal system by Samuel Kolb is basically, well, you assume a form of your SMT problem. There is certain conjunctions of clauses and these inequalities with particular parameters that are appearing, and then you encode that, you encode your examples and that format into a model for a solver, and you let an SMT solver actually find the solution. And then there is like, incremental versions of that will more rapidly find the models in a sense. So a first way to learn constraints is to use a constraint solver to actually find the solutions to that. A second one is more enumerative. And here you see a technique that we've done to find these constraints in Excel sheets. It's constraints that would take the form of these Excel formulas that people find so hard to find. A lot of people working with Excel sheets need such formulas, but have no clue about how to write them. And we found it surprisingly easy to build a system called Tackle that would, automatically discover these macros, these constraints. And here you see, for instance, that certain regularities hold, like the total, for instance, is the sum of the three columns, and you can say T16, so that's the sixth column in table 1 is actually the sum of the columns 3 to 5. You can also see that there is this foreign key relation between this type that occurs in the top table and in the bottom table. And so what we did there is like really take a clever generate and test the kind of enumerative approach to find these formulas. And that's very much in the spirit of this programming by example, this kind of style of reasoning. In the first step, tackle would actually detect the tables. There is 2 tables here. It would then look at blocks. What are blocks? Blocks are kind of consecutive cells, matrices, blocks, where you've got the same type. So all numbers are all strings that are there. And then it would do this very clever generate and test approach to enumerate all possible constraints that make sense for these types. Of course, if you work with numbers, then sums make sense. If you work with strings, then sums won't make a lot of sense. And so you constrain your search on that, and you'll actually find then possibilities for that by looking at the right kind of assignments there. We've also looked at, and so that's like the second kind of technique that you can do for constraint learning. That is, you can kind of generate and test in a clever way. A third one is that you can also search, and we've done that to look at this kind of integer program problems where you have also, again, this nurse rostering, for instance, as data. And then you want to find this kind of polynomial constraints that are indicated on the right hand. And what you can do there is like do a kind of top-down search to find for constraints that hold. Of course, that's all under the assumption that there is no noise and that your data is kind of satisfying these constraints. And so you can enumerate these, but you can enumerate them in a kind of relevant manner so that certain constraints get more specific and can be pruned away if they don't hold. So what you see in the left branch of that search tree is that you add a kind of matrix variable, and if that's an all positive one, then you also know that, well, there's going to be less data points that satisfy that constraint, and so you can actually do this general to specific search from concept learning. You can actually apply that in this case. The latest that we've done in constraint learning is indicated here. It's this learning for MaxSat, and that's the most realistic and the most fancy setting, where we've got also a lot of learnability results. What you see here is like contextual examples, and that's mirroring like what you would also have in these practical situations, like the nurse rostering. In any practical situation, there would be certain things fixed for the head nurse when she has to decide, and there would be certain variables that she has to fill out. And so the fixed values give you a kind of context, and within that context, she makes a decision that is good, or that is kind of best, or that is kind of optimal. So the ultimate assignment that you will get will depend on the context. So the black is the context. The red values are then the kind of completions for that context. And the tricky thing is, if you work with this weighted MaxSat, you'll get formulas like you get like this weighted constraints, like on the bottom right. And the difficulty with learning in this setting is that if you have like a positive example, well, then of course it's optimal for that particular context. But if there is a negative example, there is two reasons why an example might be negative. It might be negative because it doesn't satisfy certain constraints. That's one option. Or it could be suboptimal. And so that's kind of this ambiguity that you have to work with. It could violate, negative examples can violate constraints, or they can be suboptimal, and it's very hard to find that out. And that's the kind of work that we've done in that setting. There is like, some ERM results and stuff like that in these papers. There's a lot of other challenges in constraint learning that you can look at. People like Stefano and Stefano Teso and Andrea Passerini have done like a lot of work on preference learning, rather than ask, is this a good or a bad schedule? You can ask like, give me something so you get a better schedule. And so you do some kind of improvements. And or you say, well, one schedule is better than the other. And so you do some preference learning, and that can also kind of speed up the learning. Okay, let me look at data wrangling pretty briefly. Here you've got indeed this ill-formatted table that you cannot provide to a machine learning system as is. So you have to do some data wrangling, and there's been approaches to cope with that. Here you see what we do. We give it like a kind of coloring. Basically, we say that the green part should constitute one example altogether and should, in a sense, correspond to one row in the table to be provided to the machine learning system. And what you then do is there is this operations that would split particular attributes, like here, this player name. It would split it on the basis of, things being bold or non-bold. You'd get like this two columns that it would be split. You could kind of do operations like filling the empty cells, and you could then also delete certain things, and then you get something that is satisfying this constraint, right? The green part is corresponding to one row, and you also see that this is something that you could input to any kind of standard machine learning algorithm. But the tricky business is now starting from the raw data, really, and the possible transformations, really to find that program that will put it into a meaningful kind of transformed table that you can then put into your machine learning algorithm. And what these systems typically have, also Flashfill has that, is like this specific operations that can be used to manipulate your data. And they will typically do a search then through a space of possible programs. They will score, of course, the partial programs that are discovered, until they find the one that satisfy all the constraints. And this is typically like an all or nothing solution. Either it satisfies all the examples, or the search, so to say, continues. And there's a lot of variations on this kind of system. You can also do this at the level of features. So far, I showed it at the level of tables, but you often get also this kind of table where, for instance, this position column has like, in some rows, there is like F, in others G, and in some cases there is both. There is like dates that are also composed of a year and the date and so on. And so also at that level, you can actually automatically transform things so that the attributes are becoming much more informative, and you get something that you can feed into a machine learning algorithm. Okay, let me skip that. The last part that I wanted to briefly tackle, and I guess Adam can, one of my students who is actually in Freiburg, can give a little demo afterwards. The autocompletion task is what I haven't really tackled yet. I've said how to transform the data into a format so that you can learn a model. I've shown how you can learn these constraints, but I haven't shown yet like how you can then learn a predictive model to predict certain of these cells. And again, there is several challenges in this autocompletion. You can look at different types of models. I'm only going to talk about one of the types of models that's a kind of ensemble of trees to make predictions. We have other models based on probabilistic programming, on probabilistic models that can cope with constraints, and also on constraint solvers. But I'm only going to focus on this one model. So this Mark system, what it is actually doing is it's learning a battery of regression and classification trees in the sense that rather than having a classical decision tree that predicts one attribute from the others, it really uses multiple decision trees and ensembles of these decision trees to make such predictions. And it's multi-directional in the sense that some trees will, for instance, predict the last attribute, whereas others will predict the first attribute, and they're actually going even further. So that's work from my colleague Henrik Blokeel, and here this was a slideshow, but apparently, with the transformation to the PDF, that has been lost. But here, what it would do is you have like 6 attributes, and some of the trees would, for instance, predict the green tree would start from X2, X3, and X4, and would predict X1 and X6. And there's quite some interesting questions that you can then tackle, like if you want to use the resulting trees to make a prediction, and if there's like multiple of your attributes that are missing, in what order should these decision trees fire? But that's like one of the ideas that you have there. Merx has also been adapted to work with anomalies and to detect them. So the idea is that, okay, you learn this ensembles of decision trees, and if the observed behavior is different than what is predicted, then these are indicative of anomalies, so to say. Okay, let me conclude this part by showing how it then proceeds. I mean, once the data has been wrangled and you want to predict these missing values, learns these macros, this in Excel is going to be called, and this is going to learn these kind of relationships, the fact that there is averages, the fact that one is a sum of the other, and then it's also going to predict, well, if you predict the average, then if you know it's an average, then you can actually fill out this 1500 value for Leonard, and then you can learn a kind of predictive model to predict the kind of salary. You can go a step further and look at this anomalies, and then you find these values that are there, and you can actually correct for that. If it's corrected, you'll get a new new results in a sense. There's quite, as I said, some alternatives for this multi-directional decision trees, these ensembles, this Merck system. There is one that more based on probabilistic graphical models, but also takes into account the constraints that are learned. There is one that's based on probabilistic programming that you can also plug in. Yeah, but that's a different story. That would be a story about this probabilistic programs, more in the style of statistical relation AI. Yeah, that's a different story. If you're interested in that, yeah, let us know, and we can talk about that as well. Okay, so I hope I've given you some overview of both automated data science in general and also of the stuff that we have been doing. I think automated data science is a broader challenge than automated machine learning, in the sense that many of these other quadrants than model building are less well defined than the model building one, and that there's relatively little work on automating aspects of that. Here and there you see things like this subjective interestingness, this particular ways of finding features in data exploration. There is this data wrangling that is getting more popular, and this transformations there. And then for what concerns our part, well, we've introduced a small but highly non-trivial auto-completion setting. It's targeting the naive end user, the spreadsheet user, and yeah, there's some original things in there like constraint learning and so on. So thank you.
All right, thank you very much, Luke. Did you want to do the demo now or take questions first?
Maybe we can do a brief demo, Adam?
Sure.
I guess I will just share the screen now.
He's trying to share screen.
So for the rest,
it is here. It says it's sharing, but it's not showing here.
Could you ask
Luke?
Yeah, to stop sharing?
Luke, could you stop sharing, please?
yeah, that's mine.
All right. Good.
Okay. Hello, everyone. So this is the resulting tool that has been developed from the Synth project that was presented. I am Luke's student, and I'm going just to quickly walk everyone here through two different small data science tasks. So the first one is just an Excel spreadsheet, and this one is about some nurses at the hospital. So on the left here, on the first column A, are given nurses, and then on the top we have the days, Monday, Tuesday, Wednesday, and so on for the whole week. And for each day we have 3 different working shifts, so morning, afternoon, and noon. And ones and zeros are basically when a specific shift has been assigned to a specific nurse in this hospital. On the top table, we have a complete table, which we can just assume that it's a schedule from the previous week, and it's complete. And this is the next, the bottom table is actually the schedule that we want to complete for the upcoming week. And here on the top right, we have the allowed hours that can be assigned per week for each nurse. The idea here is that we can learn from past data from the table on the top, and then we can use that knowledge to complete the table on the bottom. So first of all, we can actually see that these tables are not nicely wrangled, formatted. So we know that machine learning algorithms are designed to work with tabular data or attribute value data. So that's the very first thing that the user would do. So here we have the Visual Synth tool. And the first thing, it gives some of the available tasks. So it can just quickly analyze this spreadsheet, and it can say that first you have to detect some tables, and then I can work with them. So after detecting tables, we see that it gives us some state here, and we have tables at their starting cells. So we have the table A1, table X1, and A19. So the very first thing to do here, as I mentioned, it's to format the tables, and we do this by giving a very minimal input to this tool. And it's like if I click to the Emma Monday morning and 1, this is actually, if you just have a bit of knowledge to transform this to attribute value, is that every of the cells selected here is exactly one specific attribute. So we can imagine that as nurses, days, shifts, and the assignment. So after selecting them, we give what we call in this tool sketches or some coloring. This is the input, and this is all we need to give to Visual Synth to be able to format these tables to the proper format. And this means that all the selected cells with the same color needs to be transformed to a single row. Since we have the bottom table also designed, formatted as the one on the top, we can link the table A1, the table on the top, with the table A starting at the cell A19. And what this means, it just means that whatever program, whatever transformation that you do over the table on the top, just do that on the table on the bottom. So these two are linked. And on the right, we don't have to do anything with the table since this table is already in an attribute value format. After doing that, we can wrangle this data. So if I click now, it learns a program, and then it gives us a new sheet in Excel that we get the data in the attribute value format. So now again, we can see it as a new data science task. We start by detecting tables. Again, we have 3 tables, and here now we can do some actual learning. So what we can do here, this is a very specific constraint learning problem in data science, or constraint satisfaction problem, and we can learn some constraints. So now it tries. We can also see that in the states now we have some very specific learn constraints. And for example, it says that the sum of days that a nurse can work is between 3 and 6. And this is actually very easy to spot because we have here the total work shifts. So these are here in the learn constraints, multiple constraint learners are executed in the background. That was presented by Luke, and they work all together. And now we can use these learn constraints to complete our missing values. So all we have to do is basically just to say smart fill, and now it just executes these things, and we get the full completed table here. And the green color means that if it's completely green, it means that it's 100% accuracy, because these are just constraints that can be solved like that. Now I will just demo also the anomaly detection, how it works. So if I just click over the anomaly detection, we can see some coloring. And again, the easiest one to be interpreted in this case, it's on the right table, that we see that it selected the lowest and the highest value here on this table, so 3 and 6. So in background, it sees those as an anomaly, and then you, as a data scientist or a naive user, end user, you can see and reason over that if you want to change or do something with them. Another example that I want to show with the use of predicates. So this example, it's about some ice cream sales in different countries with different types, and we have the total profit of sales for the ice creams, and we have a column there if there was a profit or not. So here we also see that we have some missing values, and in this case, the user wants to complete this missing values. So again, we start by detecting tables here, and I'm going to automatically directly say like, okay, let's try to smart fill. So in this case, there is only a predictor being learned, and we can see that actually this value here, 1420, it's not the sum of the others, because the sum is 1620. And this is done because we have a very little amount of data, and the predictors are not really good at learning what's the sum here. But they can give the other category here if it's profitable or not. So what I'm going to do, I'm just going to reset, and I will be deleting this again, this data. And I will repeat. So I will detect tables. First, I will learn constraints. And in this case, now we can see that in the actual state, we have this capability that the constraints can learn that the values from F2 to F25 are actually the sum over the columns from C2 to E25. So now if I try to smart fill, we can see that we get the 620, the exact value. So here is a typical use of the auto-completion module of the Synth project that combines predictors and constraints all together so they can give the best of results. One very useful thing about data engineering and other things together with the data exploitation is that if someone is interested to do some smart select and some pre-processing, we can give some example by colors. So I'm just going to color the yes with a green color, and I will be coloring 2 examples with a red color. So now if I give to Synth this little information, I want to use this so that it can learn a way to select the specific data that I shown for the old tables. So now if I run this, it will automatically color these things, which the user can repeatedly do some more data science tasks over this thing. One thing that I've shown in both cases, but I didn't mention, is that actually both tables are in a relational setting. So it also is capable to see that there is a foreign key between the table A2 to A25 and A29 to A32. So chocolate, banana, speculoos, and vanilla, which means that the constraint learners also use information from other tables. So it's not only tabular data, but it's also relational data. Also, the same is for the nurse example, which uses the total work shift. So if I would be going now over Lucas here, Lucas should have some. Okay, so in this case, yes, because this is given, Lucas have a sum of 0. So if I would be deleting those input here and then smart filling again, I should get a 6 here. Okay, in this case it's 3 because it does over everything. So it also respects the data from the other table. So with these 2 examples, I just gave you a very brief workflow of this tool, but the tool and other information are available in our website. So just search about Synth KU Leuven, and you will see the manual and other tasks there and paper related to this work. And I guess now we can continue with the questions.
Maybe you can stay here.
I guess it is.
So, questions for Luke or also Adam? Just begin.
Can you hear me? Hello? Can you hear me, Luke?
Yes.
Luke, can you hear us?
Hello?
Yes, I can hear. Yes, I can hear you.
Okay.
Can you hear me?
Yeah, I can hear you fine. I guess I have 2 questions. Maybe I'll start with a more concrete one. So, I mean, you talked a lot about data wrangling, and I mean, one problem is that for AutoML we kind of have a fully specified, I don't know, optimization problem, so to speak, and for your scenarios, that's largely missing. Yeah, so it's either not there at all or partially there. So isn't it then like super important to enable the data scientists to review what your automatic wrangling approaches produce? So he or she can kind of check that. Do you have any, maybe I missed that a bit during the talk, or do you have some ideas or comments on that? So I guess, don't you have to explain to the data scientist what your automatic wrangling systems have been doing, so that person can then either, I don't know, potentially reject those or intervene, or be super happy about that everything is correct and at least matches either that partial specification or that, I don't know, internal specification that that person has in mind. Does it make sense what I'm saying?
Yes, it perfectly makes sense, and in a sense that's also what we are trying to offer. I mean, you've seen these colorings that Adam briefly mentioned. So the way of, well, one way that we found quite convenient in interacting is like marking things in a particular color, like good and bad things in green, and bad things in red, for instance. And that's actually relatively minimal intervention that you have to do in order to give extra constraints to the data wrangling. If you see that certain things are not wrangled correctly, you mark them in red. If you want certain properties to hold, you mark them in green. And you can continue like that. But the idea is really that you work with these kind of simple constraints. We have also like done other things like trying to find types in these spreadsheets, which in a sense also can be perceived as, you know, a type is like coloring, and that's quite useful as an interaction. But it's true, it's the kind of interaction and trustworthiness is like why all my co-authors of this paper in CACM say, well, you should never fully automate data science. You cannot trust it. You really want to see what's going on inside, and yeah, I think that's really important. That is ways of verifying that.
Thank you.
Other questions? While the mic is making its way, quick follow-up from me to Bernd's question. So would it also be possible for the user to look at the logical formula and say, well, this constraint here, no, actually, that's not quite right. This is too loose, this is too tight, etc.?
Yes. So that's the advantage with the models that we've learned, you know, for combinatorial optimization and for constraint learning. You can really inspect these things, like you can inspect like these macros that you find in Excel, and of course you can also correct them. You can indicate that certain things are undesirable, or of course that requires that you understand the language in which these things are written, which might be hard for the totally naive end user. But at least a lot of people can understand constraints, and in some cases you can even write them down in almost natural language, these logical constraints. So that's certainly an advantage. Yes.
All right, thanks. Next question.
Hello. Have you done any studies with users, or with the naive users, or are you planning to do any studies?
Well, we have done some preliminary studies at the end of the project. We're always looking for volunteers, and I'm sure that Adam will be very, very happy if there's a couple of volunteers amongst you. Of course, you're in no way naive. You're like all experts in machine learning and things like that. But I'm sure that if there would be people willing, because we have some numbers, but not enough end users to draw conclusions right now.
All right, thank you. Next question is over here.
Can you hear me? I have two questions about the learning by example. You showed that recurring example. So, and my question is, what other tasks could be automated the same way? And the second question, what kind of algorithms you use in the background to apply to detect the transformations that happens and replicate them again?
So I guess this question is for me.
Yes, so the programming by example is typically, I mean, there's like the difference that Sumit made with his flash fill is now pretty well accepted. Like I was doing program synthesis, you know, in the 90s, and I got frustrated. I really gave up, and I thought this will never work. It will never do anything useful. And there were others like me until like in 2011 or 12, I saw this work by Sumit, and the change of thinking that he made is like, first of all, he looked a lot, he spent months like looking at concrete problems in Excel sheets where people were saying, well, this is the kind of functionality that we would like to get, the kind of thing we would like to do, but we don't know how to do it. And secondly, rather than looking for general purpose programs, you look for programs that are in a very domain-specific context. And so it's, in a sense, very specific programming languages that you use for doing that. And that means that, you know, the search and the complexity is reduced enormously. And secondly, there's also like lots of heuristics inside these systems that have been trained by looking at many problems, and that really make that it works for these problems. Yeah. So it's a combination of like a few hard constraints, intuitive examples, a very specific context, and this strongly biased language, you know, this domain-specific language, in a sense that that's pretty restrictive and very tailored to the task. But they have like, I mean, there's a series of programs that his group has developed over the past, you know, 10 years. It's really impressive. I mean, it's in Excel. People use it on a daily basis. It's also with this data wrangling, there are interesting techniques where you can, from a few examples, can give can produce interesting transformed tables. And the latest is really looking at this more semantic transformations, not just the syntactic ones. And that's also coming up. You can be sure about that. 5 to 10 years from now, some of these semantic transformations are also going to be provided in there. The examples are really interesting. If you want to find out more about that, I'd recommend you to either go to this Sint website where he gave a talk, and he also was also keynote at the past ICHCAI, and that talk should also become available in the next few days or weeks online. That was also a very interesting talk.
Right, maybe one final question.
Hello. Yes, super cool. I really like the integration of Excel and why you have there and everything. One thought that I had during it is there was a section where basically you did the autofill on one of the columns, and basically, you know, you said like, oh, it is incorrect because it's not very good at adding like the things together. Then you did the constraints, and then it was correct, right? But both of the times it just highlighted up in green, like, oh, we're good to go. This is good predictions, right? Do you have any indication to the user? Like, I know, like it was mentioned, like the colors, but for example, you could do like cross-validation to figure out what is your expected accuracy, what's your RMSE expectation, and things like that. And highlight to the user to keep them honest. Because otherwise, if you give this to an economist or something, and they have a job to do, which is filling in these columns, they're gonna be like, well, look, the color's green. Good job. Send it down the pipeline, right? How do you like keep them honest? And yeah.
Also, that is a very good question. And indeed, in some of the models, we've actually indicated the kind of confidence that we had, like mark the predictions, you know, in a particular color, yeah, redder would be like less reliable, and greener would be more reliable. So that people can really look at those that they trust the most, and indeed we've done that using cross-validation. That's in the Psyche paper. Yes. So that's a very good suggestion, because you ultimately want this reliability to be indicated to the end user. Yes.
Well, also like communicating how difficult the problem is that you're trying to solve, right? Like, for example, are you getting, you know, 70% accuracy in cross-validation versus 98%? Could mean very different things in terms of the usability, right?
Yes.
And the user knowing that would then kind of inform them on if they should trust. Yeah.
Yes.
Very cool. Very cool. Thing that you created.
Maybe just a small comment on this. It's that we explicitly let to learn the constraints and the autofill separately, so you can actually see the power of synthesizing inductive models all together. But in the last, like, I don't know, production version of this tool or something like that, you would just have like detect tables, not even that, or just autofill. So that's like the ultimate goal. And in the background, I guess you do something what it was presented today, like you have your architecture with multiple stacks and ensembles, but in this case, we are using constraints learned and also predictive models on the other side that are perfectly fine to live together in the same environment.
Oh, absolutely. I'm more talking about the evaluation of the values you are ending up
Yes.
filling, right?
Okay.
And like getting an indication of how good you
Yes.
expect those values are for reality, right? But yeah. Thanks for that.
All right, then we're at time. So let's thank Luke again. And I'm sure if you have more questions, Adam is right here. Luke, fire him an email. And for us, it's lunch now.
Okay, thanks. Bye.
Bye.
Thanks, Luke.